So good afternoon, everyone. Today I would like to present an introduction to the sampling rate calculations from the passive assemblers using some MATLAB code. And I think this topic will be very suitable for our lab members who are interested in the atmospheric monitoring. As you know, in order to collect the atmospheric pollutants, the high volume assemblers is widely used. However, it requires electricity, and sometimes it is very expensive in operations. Therefore, in some cases, we use the passive assemblers. With passive assemblers, it is low in cost and simple in operations, and it is suitable to investigate the local sources of air pollutants. However, with the passive assemblers, we need to investigate the uptake mechanisms of the air pollutants on the absorbent. In these figures, you can see that in order to, before reaching the equilibrium state between the atmosphere and the absorbent concentrations, the accumulations of the pollutants have to pass two phases. The first one is the linear phase, and the second phase is the non-linear. After that, the air concentrations from the passive assembler can be easily calculated by dividing the accumulation amount on the absorbent by the total air volume. However, we have two cases here. The first one is the linear phase uptake, and the second case is the non-linear phase uptake. So for the less volatile compounds or the high molecular weight, the uptake phase will be linear, and the effective air volume can be simply calculated as the product of sampling rate and the sampling durations. Whereas for the more volatile compounds or for the light molecular weight compounds, their uptake will be non-linear phase, and then the effective air volume will be very important. You can see that in both cases here, the sampling rate play a very important role in order to convert the PAS concentrations into the air concentrations. Therefore, I prefer this reference documents. So this group of authors, they use some prediction model using the MATLAB code to calculate the sampling rate using the meteorological data. So this is the first interface of the MATLAB. You can open that and then choose the direction to these two functions. These two function code you can download from this paper. And then you can see here in this MATLAB code we have two functions. The first one is for the meteorological data, and the second one is for the sampling rate and the passive air effective and the sampling rate and the effective air volume. You can double click on these two functions and you can see the detail of functions in here. In order to run the MATLAB code, you need two files. The first one is the chemical descriptors, and I named the file is hello PAH in here. And the second one is the meteorological. For example, in here this is the I1 file, and this one I1 SR sampling rate, this is the result from the MATLAB code running. So as I said before, as I said in here, the most difficult part is not running the MATLAB code. It is all about the preparations of the data. So the first data set for the input data is the meteorological data. It is better to use the NOAA data. So you can go to the website and download the meteorological data. The second source, you can use the Korean administration meteorology using the AWS in here. For the first case, you can visit this website and then choose the hourly or sub-hourly data, and then search the city in here. In this example, they search for the Chicago city in the US, and then click on this symbol, and then you can choose the identify. When you search by the CT here, you can see some yellow dots. So this is the NOAA station in this CT. And then by the identify, you can click on some yellow dot here. For example, click on here, and then you can check the station ID for this station. And then after that, you can visit this website, choose the year of your meteorological data, and then download it. So this is the station, the NOAA station for Chicago City here. Download it to your computer and then extract to in the same folder as the two functions as I mentioned before. So another way is to go to this website and download the meteorological data using the AWS stations. So I will skip this one because it is easy for you. The second input data is about the chemical descriptors. As I said before, so in this table, the first column is the compound. So we don't use the name of the compound here, just put the number 1, 2, 3, 4, 5, and this molecular weight. These two boxes show two different approaches. The first one, you can provide the log KOA value, the octanon air partitioning in here. And the second approach is to provide the linear free energy relationship. For the first one, the log KOA here can be calculated by this equation, A plus B over T. T is the ambient temperature. A and B is the other slope and intercept, and you can check this value from the previous study. For this column, this is the internal energy. The delta UOA can be calculated as the Lagrange pair of 10 multiplied B and R. B is here, and R is the gas constant. For this approach, you can also check the value for ESABVL from the previous study. And then after that, we can run the MATLAB code in here. So this is the example for the Ulsan city. I searched in Ulsan, there is one NOAA station in the Ulsan airport. And then this station is in here. So this is the file downloading from the NOAA extract, and we have this file. The next step is we can type the name of the first functions here. And then we put the station number here. And then this is the start year. I choose 2013 in here. And then the total number of year, just 1 year. And then enter. You will have this file. This is the result from the first running code. Double click on this file, and you will see this is the result, meteorological data. The first column is the date, year, month, day, and hour. This is the temperature, pressure, wind speed, wind direction. And this one is the water vapor mixing ratio. So if you use the NOAA data, it is easily to calculate and use the MATLAB code to have this file. However, if you use the data from AWS, you cannot run the MATLAB code in here. And then you have to calculate everything in the Excel file. And you can check on the equation in here, in the MATLAB code here. So you can go down and then check on the equation and then calculate by yourself in the Excel file. And then after that, we can use the second function to calculate the sampling rate. The first one, we need to edit the output file name. Here I use R6 and sampling rate. The second one is to choose which approach did you use for the chemical descriptors. As I mentioned before, we have KOA approach and LFER approach. In this case, I use KOA value, and then I put in here. The next step, we need to specify the detailed information of the absorbance. In here, the puff informations like diameter, thickness, dpuff, and the areas. The next step, we can type the second functions. And then this is the start time of the sampling durations, the end time. This is the station ID, and this is the meteorological data, as I mentioned before. And then enter, and you will have this results file. Double click on this file, and you can see this is the results from the MATLAB code running. First column is the station ID. This is the start time of the sampling duration, end time, the total hour of our sampling durations. The first row here is the effective air volume, and the second row here is the sampling rate. So this is all for the MATLAB code running. So the most important thing is not about running the code. This is about the prepare the input data. And that's all for my presentation. Thank you for listening.